Hello and welcome to this quick one on halogen displacement, this time via a leveled response question. So as always, we need to do a quick plan before we get started. So the first thing to do is to isolate the commands, the instructions. The second is to isolate what they're asking you to describe and explain. And the third is to be mindful of any details that they give you, such as the fact that cyclohexane is being used in this particular case. So in the box, I've put forward a few ideas that you might want to think about just before starting. I've put the reactions, or the reactants at least, together in equations at the top, and I've put a cross by the one that won't work, and a cross by the one that will. So because the question asks you not only to describe the reactions but to explain them as well, I've popped something in about bromine being able to oxidize I-. The reason being the explanation that there's less shielding in Br. Now that stuff in the box on its own is not an answer. Clearly I've got to now organize it into an answer that matches what they want me to say. So, in terms of what I've got to do, I've put down a section that allows me to put the observation down, a section that allows me to just explain what's going on there, and a section that allows me to put an ionic equation for any reactions that occur. So let's start with bromine and potassium chloride. Obviously, bromine is less reactive than chlorine. You remember that from GCSE, so therefore it's unable to oxidize or displace chloride ions from solution. So therefore there's no visible change, or you can say the solution stays orange. So obviously we can put down a reason based on our GCSE knowledge that bromine is less reactive than chlorine. The A-level reason, there's more shielding present in bromine, so therefore bromine is unable to oxidize chloride ions in KCl. Now I know it says include an ionic equation for any reactions that occur, but I thought it might be a good idea just to put one in for ones that don't occur, so you can actually clarify with the examiner that there's no reaction. Now looking at the question, before I go any further, I've highlighted at the top, followed by a few drops of cyclohexane. So, therefore, I need to say something more in my observations for this particular pairing of species. So what's actually happening as well is the cyclohexane is turning orange because the bromine is dissolving in it, even though it's not reacting. So now what we can do is look at bromine reacting with potassium iodide, or at least bromine being mixed with potassium iodide. So with your bromine and potassium iodide, there's two changes you'll see. First, the cyclohexane layer goes purple, and aqueous layer goes brown. So for the same reasons that bromine is less reactive than chlorine, it's more reactive than iodine, so there's more shielding in iodine, so therefore bromine can oxidize I- to I2 by removing one electron from each I- ion. So that can be represented by the ionic equation at the bottom. So the final conclusion we can make is the reactivity trend is chlorine more reactive than bromine, more reactive than iodine, due to more shielding down the group. Okay, so this isn't the only way to get the 6 marks in this particular question. As you probably know by now, if you've looked at the mark schemes of a range of level questions, you'll see that there's lots and lots of what they call indicative scientific points that you could make. But the main thing is that you're talking about the oxidizing ability. You mentioned the shielding somewhere. You're talking about the relative reactivity. You're linking the observations to actual conclusions in terms of whether or not it's reacting, and you're giving an ionic equation for the reaction that does occur. In other words, following all the instructions at the top. Okay, so thanks again for listening, and until next time, see you soon.